So thank you for coming. So I'm going to give a brief talk on working as part of the Remote Sensing Group, or RSG, here at RailSpace. So considering its early careers, just give you a brief overview of how I got here. So I did an integrated master's at Imperial, during which, for my master's project, I actually worked for a member of the Remote Sensing Group. I then went and did a PhD in satellite remote sensing at Monash University over in Australia, in Melbourne. And then after that, I ended up working in the Science and Innovation Group at the Australian Bureau of Meteorology in Melbourne again, before returning back here to work as part of the Remote Sensing Group. So Michelle has given a bit of an overview of this already, but I'll go over a bit more detail. So there are 10 of us working on satellite retrievals and associated computer systems, etc. So some of us work on trace gases, so methane, ozone, sulfates, these kind of things in the atmosphere. I work with Dora as part of the clouds and aerosol section, so focusing on cloud retrievals and things like dust and smoke. I see an example of this from our Viz tool here, from one of the newest satellites, the Flexible Combined Imager, FCI. Where you have this big purple area. Here is actually a dust storm over the Sahara. And also you can see here from earlier this year across Spain and Portugal, there were these large wildfires that produced all this smoke. And you can see the kind of images we deal with. And essentially what we do is we develop algorithms, so specifically the ORAC algorithm, so optimal retrieval of aerosol cloud, to pull out information from this imagery. In this case, to cloud and aerosol optical thicknesses, cloud top heights, useful information that can be used to provide more information to industry as well. And we can do this in near real time, as so for visualization and also for providing things like radiative fluxes for solar industry. We also don't just do the near real time stuff, we also do large scale reprocessing of data. So in particular for the European Space Agency climate change initiatives, but also for the climate data records. So an example of this is one of my colleagues worked on part of the Copernicus the Horizon stuff, is they now have about 0.5 petabyte worth of satellite data for one series of satellites. So you can kind of get an idea if we work with extremely large volumes of data and have pretty intensive computing requirements as well as part of that. We don't just produce data, though, we also carry out some validation and analysis as part of this. So then I thought I'd also give a brief overview of something I wasn't massively familiar with before arriving here, which is working with the European Space Agency on these kind of large-scale international projects. So in particular, this is the Hitachi project. So to give you an overview, basically, the European Space Agency will send out a tender, they get back to you, and then you get this contract, and then you work as part usually of a large international team, as it's European Space Agency. So in this case, the Hitachi project is the satellite observations to improve our understanding of aerosol and cloud interactions and associated radiative forcing using satellite data records reported by the European Space Agency's climate change initiatives. So this is Hitachi for short. We're working as part of a large group. So there's Reference, which is in Belgium. Then there's the German Weather and Space Agencies, so DW, DLR, as well as Norwegian Met Institute. Before I'd come to RailSpace, being based in Australia, I'd not really had to be able to work with large international organizations because of time differences. It's very frustrating. So this is something interesting for me. And you get assigned to technical officer, which is very useful because they're based just down the road in XCAT, or SCAT, sorry, on the Harbour campus. So the building you might have seen as you came in. And projects get broken down to work packages of deliverables, which is something, again, wasn't really used to before coming. So we, as part of this project, processed using the ORAC algorithm I mentioned earlier, data from 2020 using Severi satellite. So this is a geostationary imager. It makes these nice pictures, as you can see up here. So we produced this for all of 2020. Ends up being about 15.6 terabytes worth of data. And you can see an example of some of that data here, where we have the cloud's top height. So this ends up being, like I say, a very large amount of data, but actually on the scale of what we used to, not very big. But yeah, that's my overview of our project. Thank you.
Hi, please can you explain why cloud masking is required for satellite retrievals, or why it's useful? Obviously, it's nice to know that there's a cloud there, but for Earth observation data reasons, why do we do it?
So for us, there's two purposes. So we want to know how clouds are affecting things like the surface solar flux, or say the solar industry. So you need to know where a cloud is, so you can carry out retrieval to know how thick it is and therefore how it impacts how much sunlight is getting down to the ground. Also useful for masking out things for, in our case, aerosols. Basically anything that isn't the clouds is kind of considered potential aerosol in our retrievals. And if we want to get useful information out about that, we need to get rid of the clouds. Otherwise, we end up with this very thick aerosol, which is just a cloud. So cloud mask is quite important for this. And actually, we've developed some machine learning algorithms to work with this. So again, with DWD, we developed the Severi, also the RSG group developed the Severi cloud mask. We've also been working on things like SLSTR, which was one of the instruments actually built here at Brown.
Any more in the room? Okay, right. Well, thank you very much, Daniel. We'll move on. Wowie, what have we got here? You brought some toys. Do you want to put them on the side? This side? Yeah, that's okay. Thank you very much. Fantastic. So next up, we have got David Salmon from Magdrive.
Good morning, everyone. Hopefully you can all hear me. My name is David. I'm from Magdrive, and we're a small startup in Harwell, not far down the road from here. And we're developing high-performance electric propulsion systems for small satellites. And I have a mock-up of this here. So this is the sort of size that we're talking about. Fairly small, fairly compact, but perfect for example, the 12U satellites that we heard about earlier in some of the other presentations. And the way that this technology works is by taking electricity in from the satellite power bus. We store that internally. We then step it up to high voltage and discharge it very rapidly through a solid metal propellant. This generates a high energy, high density plasma, which we exhaust, and that provides the thrust to the spacecraft. So I'm going to take you through a very brief history of Magdrive development over the last 5 years since I joined. But first of all, why do we need electric propulsion in satellite? Actually, this video that you may have seen recently from the ISS came out very timely from this. You can see just how much traffic there is in low Earth orbit, and particularly for these new missions that we're talking about, lots more CubeSats and things like that. Collision avoidance is now a necessity. We can't just rely on a passive orbit. We actually have to actively maneuver to avoid collisions. And this is going to be even more important when we look at new orbital businesses, in situ resource utilization, in-orbit manufacturing, satellite servicing, things like that. We need additional capabilities, which we just don't have in small satellites at the moment. But currently, there's a trade-off between chemical propulsion and electrical propulsion, with chemical providing high thrust, but a low specific impulse, and consequently a relatively short satellite lifetime, with electric, which provides a much longer lifetime, but relatively low thrust. This is where the Magdrive fits in, as it's a really nice hybrid between pure chemical, pure electrical, and we can achieve some of the characteristics of both. So we started back in 2019 when our two founders, not here today, unfortunately, developed the first working prototype, which I have here, and I will have all these toys for you to come and see later. So as you can see, relatively sort of haphazard, hand-built, and it was enough to get them the first funding, which allowed them to hire myself and some of my colleagues here today. But then, progressing on from this, the engineering that we did from there was to take the concept and develop the first sort of lab-based models. This was very much a research phase, as we still are today, testing out what works, what does the architecture look like, how are we going to get it to work. After that, we developed our first full system. Part of that is here now. So this was the first Magdrive that you could pick up and take to a conference and say, hey, look, this is what we're developing. This is a propulsion system. Obviously, this has now been hacked to bits, but it was a really useful exercise in building a system that was fully contained, and we could instrument it and interact with it on the test stand as well. And then since then, we've been working on scaling the size down, increasing the power, increasing the reliability. So this is from 2023, this board here. As you can see, it's still relatively large, not in the form factor we're finalizing yet, but it allowed us to get the whole system up to the power that we wanted to try. And then this is where I run out of actual models because they've been taken away from me. But in 2024, we developed our first fully to scale model, which was the entire power system in this form factor. And then I think we're on to the last minute, pretty much perfect. We then developed this full system model, which we launched on the SpaceX Transporter 14 mission in June this year to scale. So not very big, but this allowed us to demonstrate our system working in space and get the information back that we need to develop the system further. So it's been quite a busy period of time at Magdrive, really. You know, it's taken us only 4.5 years really to go from initial lab concept to first flight, which is really exciting and we really enjoyed it, but it has been challenging and there are plenty of engineering challenges still to overcome, particularly things like reliability. I don't know how many of you are engineers here, but this is always one of the big things, and I know quite a few people here working on similar projects here. So it just shows how quickly startups are able to move in the new space industry. And I always like including this slide, where we're going in the future, because it really highlights how important propulsion is for the new space generation. Being based on a metal propellant, this is abundant in the universe, in regolith, in other debris, and we can always look to use things like defunct satellites as fuel for Magdrives. So not only are we avoiding debris, but hopefully we can help mitigate it as well and try and reduce the amount of debris in orbit. And we're working with various partners on that. It's also shelf stable, inert, and safe to handle, which simplifies integration for satellites and means that it reduces costs and helps with expanding access to the market. So thank you very much for listening to me. If you have any questions, please come and find me at the poster stand later if you don't get to ask them now.
Next. Yes.
Thank you. Very interesting presentation and great toys. What's the main purpose of this? What the main idea of the thruster? Is it more for orbit raising, lowering, or station keeping, or can be used for both? Or how do you see it?
Yes, it's a really interesting technology from a theoretical perspective because it can be used for both. The way that we work, these high voltage discharges, they are single pulse events. And we can change the characteristics of those pulses by changing the energy in the pulse, the voltage, and things like that. And what that allows us to do is vary the performance of the propulsion system. So we can achieve high thrust, low specific impulse maneuvers for things like close proximity operations or, like collision avoidance maneuvers, sorry. But we can also then change those parameters. We can increase a specific impulse at a loss of thrust, of course. So then it targets the more traditional electric propulsion regimes where we can do things like long duration station keeping or slow orbit raising maneuvers as well.
Deorbiting as well, potentially?
Potentially deorbiting, absolutely, yes. It's effectively orbit lowering to avoidance purposes. And this is something that we've developed previously as well, we've explored as well. So it's a very versatile system, and it should be, in theory, when we get it all working nicely, it should be a really useful system for satellite manufacturers.
Thank you very much.
Final thoughts?
Thank you for the talk. How much of an improvement in terms of satellite lifetime this provide versus conventional systems at the moment?
Can't give you a specific number for that because it depends so much on the mission parameters. For example, if someone wants to just use it for station keeping, that's very high specific impulse, low thrust over many, many cycles. That could be several years, whereas chemical propulsion isn't really suited to that. So there's not really a specific answer. I can't say, oh, it doubles the lifetime of the satellite. But what it does allow us to do is increase the satellite lifetime sufficiently that it then reduces costs, prevents having to launch new satellites and things like that. So it's all a sort of like an integrated approach to it.
Hi, everyone. My name is Jessie Alexander. I work here in RAL Space, specifically at CEDA, which is the Centre for Environmental Data Analysis. I'm going to be talking to you about my graduate placement, which was using machine learning to model and predict wildfires in Scotland. So a bit of context. If you don't know, at SCFC as a graduate, you get a chance to do a graduate placement. And this is a great opportunity to go and do something different to your usual role. My role involves kind of a lot of communications and outreach and kind of interacting with our users. We provide our users with a lot of environmental data services. We have a data archive, which we store a huge amount of environmental data on. And we also have Jasmine supercompute facility, which we allow scientific and environmental researchers to access to do their environmental research. Part of my role is trying to improve those services and trying to make it easier for users to use our services and our data. So when I was thinking about my placement, I was thinking, if I want to improve these services, I need to actually understand how a user might go about using our services, how they find it, what their kind of journey would be. So I really wanted to essentially be a researcher and do some environmental research for my project, which is why I ended up at the University of St. Andrews. Another organization that we're really closely linked with is the National Centre for Atmospheric Science. And they had just opened a new research centre last year at the University of St. Andrews, which was using AI and machine learning to basically enhance climate research. And I saw this and was like, yes, let's do it. So that's a bit about how I got there. You might not necessarily associate Scotland with wildfires. You will see that there are some concerning trends with wildfires in Scotland, with quite a severe increase in the past few years, not even including 2024 and 2025, which are actually much higher. If you saw earlier this spring, there was a lot of wildfires in Scotland. And you can actually see in the kind of seasonality, which is what kind of makes Scotland stand out from a lot of other European countries like France or Spain or Greece, where there are wildfires. Those are kind of normally more in the summer months when it's just hotter temperatures. So actually it's quite interesting that most of the fires are in springtime. And I'll hopefully be able to tell you a bit about why that is essentially. So one of the first things I did was looking at some land cover recategorization. So part of the data that we used to look at these wildfires was what type of land cover they are, essentially where they are and what type of terrain is around that wildfire. So initially we kind of have loads of categories, not really helpful. You know, you've got some really specific ones. So one of my initial jobs was essentially just kind of combining these into more kind of general categories, not only to kind of help the model, but also just kind of ease understanding a little bit. You know, there's not really a need to kind of understand how airports affect wildfires, but if we kind of just combine that all into one urban category, then we end up with something like this, where you've got kind of more simplified categories, and that's kind of, that then feeds into our model. So if we move on to that, so we take our land cover data and we combine it with these other kind of data sets. So these are all data sets from AO5. We've got things like human activity, power line density, road density, topographical data, which is about the actual geography, like the slope and which way it's facing. Those ones that I've all talked about are static data. It's static data, so that doesn't really change over time. But then kind of probably one of the most important ones you would say is weather data. So things like temperature, wind speed, relative humidity, precipitation, those all feed in as features in our model. And then what we do is we've got another data set, which is EFIS, which is the European Forest Fire Information Service. That's kind of comes under the Copernicus program. And this is just a data set which has actual wildfire occurrences, specifically where they occurred and when they occurred, so the date and time. And essentially I just can kind of combine these. So we've got the wildfire occurrences and then those features essentially describe and depict information about the wildfire. So we take our final data set, we pop it into our machine learning model, and then we get the result of wildfire predictions. I'll just talk you through a little bit about how we get there. So we take our wildfire ignition points, which is essentially our data set with all of our wildfires. So you see, time and place. What we do, so we've got those ignition points, and then we need some kind of general ones for when there weren't wildfires. So we take an equal number of points, which we randomly select, a random date, random time, and random location somewhere else in Scotland. And most of the time, there isn't a wildfire there. So we've got an equal number of like data points in our data set, which is when there is a wildfire and then when there isn't a wildfire. We combine these into our total data set. And then we split. If you're not familiar with machine learning, this is a kind of pretty standard way. So we split our data set into training data and test data. We separate the kind of classifications of the test data. And then we put our training data into the machine learning model, run the model on the test data, and then it kind of spits out predictions. And we compare that with the actual classifications of whether there was a wildfire or not. And that essentially becomes the model that then is used. You will give it the information, and then it will use that to essentially predict whether there is a wildfire there or not. It runs through a lot of different machine learning algorithms, and then you get your completed learning model. I don't think I have time much to talk about these SHAP values, but these are the one results that I'm including because they essentially highlight the importance of the different features. So the ones at the top are the most important ones, things like relative humidity and precipitation, and essentially how far they veer away from that line is how much they affect the model. So veering off over to the left means it's going to decrease the chance that it predicts a wildfire. Veering over to the right means it's going to increase the chance that there's a wildfire. Sorry, that was a very quick whistle-stop tour. But yeah, that's my presentation. Thank you.
I think we'll just go with the one question for now. We'll go right to the top.
Great presentation, thank you. I just wanted to know what kind of findings from your placement you're taking back to the work that you do here at Valspace.
Kind of one of the big things I had is working at CEDA, we kind of get to know all the kind of nitty gritty details of all the data sets that I'm working with. And we've got a lot of support in terms of how to use Jasmine, maybe how to like download a file, but there's actually kind of not that much support, if any, in terms of actually looking at data or like the actual data files. So I find it quite hard to like something like a geographic data set will have a coordinate reference system, but quite a lot of the different files will have different ones, converting between them, understanding if a data set is multidimensional, some of those dimensions are coordinates, some of them are time, and actually trying to get to grips with that was really quite tricky. And I felt like, I have all this data, but it was kind of shocking to me that I didn't necessarily know that or understand that. And it was quite hard. It felt like quite a steep learning curve to actually understand the way that that data is structured. So to bring that back, I'm trying to think about ways that we can make it easier for people to kind of, I suppose, break the barrier. If you already know in an environmental science, you might already know this, but for kind of someone like me just coming in, it was quite tricky. So trying to make it easier for people to kind of understand and get to grips with the actual data set. That's kind of a big goal from my placement. Thank you.
Hello, everybody. I'm working at ESA as an intern. I joined 3 months ago. I'm working on a gecko-inspired adhesive. I'm going to talk a little bit about that. So what is a gecko-inspired adhesive? If you look at a gecko feet close up, we'll see a bunch of hair-like structures at 5 microns. And if you zoom in even more, we'll see structures called spatula at the ends of those hairs called spatula. And those are like 100 nanometer scale. So gecko, or the animal gecko, uses these structures to climb instead of using suction, which is what scientists thought it was, first of all. So how does this work? So first of all, friction, but there's another mechanism called van der Waals forces, which come into play. So when there's a gecko atom close to a surface atom, due to quantum fluctuations, sometimes electrons are on more side than compared to another. This then polarizes the atom next to it, which creates an attraction called van der Waals forces, right? This is a very small force initially, but because there's so many structures in the gecko feet, it becomes the main mechanism that gecko uses to climb. So what I'm doing here is, well, they already tested this in space. They sent a UAV called Astra B, and it uses a gecko-inspired adhesive as a robotic gripper to grip onto surface in the ISS. So what my internship kind of encapsulates is I want to test this material in low Earth orbit. So I have to simulate low Earth orbit conditions. So I made a test plan for a thermal vacuum chamber, and I have 2 categories. One adhered to a material, and other one is detached to a material. These categories will have these sample groups. I'm going to do 100 cycles in total, but I want to see how the degradation kind of goes. So I'll have a group of samples that will be removed after 25, another group after 50, another group after 100 cycles to see what happens. How I'm going to characterize this degradation is using SEM imaging and performance testing. So right now I done some initial SEM imaging and also performance testing, and we can see some pretty pictures. This is under an electron microscope at 100 microns. These are two gecko structures that are about approximately 60 microns apart. There's a bunch of them in this sample. There's another one. This right-hand side one is a sample I used to show my colleagues what this structure is. So it's a bit very dirty, a lot of dust particles, and there's even a structure missing. And the left one is a clean one, which I'll be using in the TVAC. The initial performance testing showed that a 2x2 sample, 2 centimeters by 2 centimeters sample, is able to have a pull force of 2 kilograms. So after 2 kilograms, it detaches, but it's able to carry 2 kilograms, which is very promising. So the context I want to use this material is in docking in space as a soft dock mechanism. So I'm working with 2 other colleagues here at ESA to kind of think about and design a docking mechanism for this material. So the next part of my project is actually conduct TVACs, which I'll hopefully be doing next month, and then followed by an SEM and performance testing to see what happened after the TVAC. Analyze the results, compile them in a report, and in the end, design a 3D printed, possibly a model of a docking mechanism with gecko-inspired adhesive in mind. And I want to extend this test with an atomic oxygen, because at low Earth orbit, there's a bunch of them which messes up with the which messes up the plastic kind of, what is it called? Nature of this material, and causes a lot of degradation. But yeah, that's my internship.
Wonderful. Thank you very much. We've already got 2 hands down up front. Sorry, actually.
Cheers. That's really cool. Yeah, just interested to know, have you predicted what you think the vacuum effect will have on the mechanism? Because friction, I guess, is normally improved by being in vacuum, and the van der Waal shouldn't be affected. But do you think that the vacuum will change things compared to on Earth in atmosphere?
I don't think so, because gecko doesn't use suction or any kind of air to walk ceilings or walls. So I don't think that will change the kind of the performance. But the one thing that could happen is outgassing, because this is a silicon-based material, might outgas, which might change its structure. So I'm also testing for that to see.
Hi, great talk. I was just wondering, your like orientation, they're all like circular.
Yeah.
Have you thought about different morphologies as well as because you're looking at obviously surface, like the surface structure as well. But have you thought about different morphologies as well? Maybe that would have an effect on like how much load it could keep. Obviously degradation stuff. You've thought about that.
Yeah. Ideally, because I mean, an actual gecko feet, the structures are much longer than what we have here. So if it was a longer structure, it would probably perform better in terms of friction. But I think the limiting factor is manufacturing. It's hard to manufacture a material this small and this kind of repeating pattern. I didn't personally manufacture this. I found a company who, manufactured and asked for samples to do testing on. But I haven't thought about different kind of shapes other than circles. But yeah.
I was just thinking larger surface area might be better.
Might be bigger. Yeah, as you said.
Wonderful. Thank you very much, Emre.
Thank you.
Okay. Next up, we've got Harsimret. Fantastic. Over to you.
Hello, everyone. I'm Harsimret, and I completed my master's in astronautics and space engineering, and now I'm researching in the field of mission analysis and astrodynamics. And I'm here to give a talk on mission design to satellite operations, a mission analysis framework for new space startup. The term new space has evolved beyond just describing a new generation of satellite space companies. As shown in the chart, the commercial space economy has grown much larger than the government space budgets, which gives rise to new space startups. Across the globe, we have seen a rise in startup culture that promotes try fast, fail fast. But in space, failure is too costly, both financially and strategically. So instead of trial and error, we need a culture of discussion, design, and discipline planning. So when you have a brilliant idea for a space application, what must you think to make that a reality? So there are some typical areas that are, and parameters that define and drive your mission. For a typical space mission, these are some of the areas you should focus on. In terms of mission objectives, we try to answer, what are we trying to achieve? For example, are we saving lives, or are we delivering 5G connectivity directly to the phone? Some of the critical requirements, we answer questions like, are there any government regulations we should meet? Are there any investor constraints or environmental constraints about our design? And then for mission concept, we'll decide that how will we deliver this data and how will we get it? What is the business case for it? In terms of subject, we answer questions like, what are we trying to look at? Is it Earth observation? Is it communications? And the type of and complexity of payload is determined by our answer to the subject. And here we answer questions like, what is the spatial resolution that is required, or ground sample distance if it is a Earth observation mission? And one of the most critical parts of a space mission is orbit design. Because once we have defined all these parameters, we look at where in exact space should our satellite be. So in terms of orbit, we answer that, do we need a specialized orbit, or one of the readily available orbits like geostationary or sun synchronous? Is it a single satellite or a constellation? Once we have defined these parameters, the question becomes, how do we design the orbit? So a typical strategy for designing the orbit is, first we establish which type of orbit are we going in, Earth reference, space reference. Like if we want to look at a particular location on Earth, we go for a geostationary orbit, but it's too far away for Earth observation. Hence, we have to deploy a constellation in low Earth orbit to get our goals. And then we determine orbit-related mission requirements, like what kind of altitude are we going for. If we go for a lower altitude, we get good resolution, but our swath width is reduced. And then we also determine what inclination and other orbital elements are best for our mission. And then we evaluate orbit performance, that how much Earth coverage is provided by our set orbit, and what are the distance from our target that we are trying to look at. And then we establish delta V budgets, that how much of propulsion propellant do we carry for station keeping or end of life procedures. What are the launch costs? So as you know, that most common way of launching for new space startups is ride shares, and ride shares only go to a specific orbit. Hence, we have to be proactive in defining it beforehand so as to minimize our launch costs. And this is an iterative process. We need to simulate it again and again, because as you know, space environment is not much predictable, and we need to perform the best simulation before we actually put it in. So hence we use some mission analysis tools like ANSYS and GMAT. ANSYS is the industry standard, but it's very expensive. And GMAT is a graphical user interface and free to use. And then once we have our satellite in orbit, we have like Operations becomes one of the critical mission phases. It involves a collection of tools and processes that plan and manage both space-based and ground-based assets. We need to perform payload scheduling and spacecraft scheduling and real-time command and monitoring. Hence, as space is becoming easily accessible, that also means that satellite operations and responsible behavior are more critical than ever. Proper operations and end-of-life management help reduce collisions and protect our assets. And hence, thank you for your time. If you have any questions, I'll be happy to answer them. And feel free to connect with me on LinkedIn so we can continue this conversation. Thank you.
Wonderful. Thank you very much. We've got time for one for this one. Fantastic.
Thank you for the talk about spacecraft operations. So what kind of answers does your framework give on the operations? Like what to do, how to do them? I didn't fully understand that point.
So it says much about, so my talk is targeted towards people who have ideas and they say, oh, let's put it in space. And they don't have much information on how to do that. So my slide answers the question that where to begin and how to think in terms of. Yeah.
All right, thank you.
And let's have another round of applause, please, for Okay, fantastic. Next up, we have got Carla coming down.
Hello, my name is Carla. I'm an MSc Advanced Machine Learning student at the University of Bath. My background is in applied artificial intelligence, and my work focuses on bridging simulation and reality through AI-driven robotics. Today, I'll be sharing how my undergraduate project, AgriBotSim, evolved into EnviroBotSim, which is a scalable AI system designed to support sustainable planetary monitoring from crops to coral reefs. So a bit about me. So as I said, I am studying an MSc Machine Learning at Bath. My undergraduate degree was Applied Artificial Intelligence. So why EnviroBotSim? AI and robotics have incredible potential to revolutionize how we monitor our planet. Traditional environmental data collection is costly, time-consuming, and often unsafe, especially in remote or underwater regions. EnviroBotSim expands upon AgriBotSim, applying those same intelligent simulated principles to new environments, land, water, and even space analog contexts. There is a clear market gap for scalable autonomous monitoring systems, and the UK Space Agency's recent funding for environmental robotics shows this research is timely and relevant. So why and how? EnviroBotSim is designed to automate and enhance data collection. It starts in simulation. MATLAB Simulink generates and tests control logic before real deployment. The system uses a convolutional neural network for image analysis, detecting things like coral bleaching or pollution, while sensor fusion through an extended Kalman filter combines pH, turbidity, acoustic, and temperature data. The robot follows a grid-based waypoints for full coverage and is scalable for multiple environments. Key benefits include lower costs through automation, reusable modular hardware, and intuitive dashboards that make technology accessible even for non-technical researchers. Data utilization and impact. So the data generated can be used in multiple ways. It provides environmental insight in identifying pollution, temperature changes, or biodiversity trends over time. It also supports predictive modeling, enabling early intervention for problems like coral bleaching or eutrophication. Sorry about that. These results can be integrated with satellite and GIS datasets, helping inform environmental policy and sustainable development planning. I've been inspired by the work of Peter Cork, whose philosophy, bringing robots into the field, aligns with this project, and by Bath's own Hydro Robotics and UK Space Agency's environmental missions. Future applications, as said, include coral reef restoration, water quality monitoring, and planetary analog testing, where robotics developed here on Earth could help us explore and protect environments beyond it. EnviroBot Sim shows how AI, robotics, and simulation can work together to build a sustainable, data-driven future for our planet. Thank you for listening. If you have any questions that I won't have time to answer, find me on LinkedIn or at the poster. I have a poster for the poster session. Thank you.
Fantastic. Got time for 2 questions with this one? Any from the room? Any from online, Anna?
Thank you. Lovely presentation. So at the moment, I think you'd be right in saying that about 5% of the oceans are or known or explored. Do you see this technique helping that percentage grow in the coming year?
Absolutely. Sorry. Absolutely, yeah. So this whole idea kind of came from, I've scaled it down to AgriBot Sim for monitoring agriculture, which I can talk about at the poster. But yeah, definitely. So the idea was to monitor environments that are really hard to reach for human beings and dangerous and costly to get you there in the first place. So yeah, definitely that is one of the missions.
We have time for one more on this session. Okay, we'll leave it there. As previously said, Carl's got a poster up, so if anyone's got any more thoughts, then they'll be around at lunchtime. Thank you very much.
Thank you.
And finally, for a little bit of a change, we actually have a team from OrbitFab coming down. I'll give you both microphones so you can sort yourself out. Just try not to bring them together.
Thank you very much. Hello, we are some of the graduates from OrbitFab, and we're here to talk about refueling in space. A little about us. So I'm Dana. I've just graduated from Imperial College London with a master's in aeronautical engineering, and I'm now a fluid systems engineer at OrbitFab, otherwise known as a space plumber. My main role is my main role is supporting the analysis and testing of fluid systems. So that's developing refueling technology for ourselves or supporting client projects.
Hello, my name is Shreya Ramteke. So like Dana, I also studied aeronautical engineering at Imperial. I'm a graduate mission systems engineer here at OrbitFab. So that's essentially working on the in-house mission analysis tool and adding new features to it. I also recently joined, so I've only been working for just over 2 months.
Hi, I'm Orla. I'm also a new graduate, only been here for 2 months. I am a recent graduate from the University of Southampton, where I studied physics with space science instead. And I came to OrbitFab this summer through the Spin Turn program, but stayed on after my internship. And now my role is in the missions and systems team. So also working on our analysis tool and the refueling platform design. So who is the rest of OrbitFab? OrbitFab is a US company that was founded in 2018. The UK side was only established in 2022, so we're very new. We're now 21 people, and we're based here in Harwell, just over there somewhere. The US side has had 2 successful missions so far, one of which was a resupply of water to the ISS. And on the UK side, we're still developing the technology to be applied in the European space sector and are expecting our first missions soon. Now, our goals. OrbitFab envisions a future with a permanent human presence in space, where manufacturing has moved off-world and there's a bustling in-space economy. This requires, though, an infrastructure that is sustainable and reusable, which doesn't really apply to the current space landscape. So OrbitFab's mission is to establish a propellant supply chain to support this presence. And the first step in that is enabling refueling for current satellites.
So how are we going to do this? The base architecture is a shuttle equipped with our active refueling interface, GRASP, or the US version GRIP, which can then dock to a client satellite. And this is ready for refueling with our passive interface, RAFTI. RAFTI allows refueling on the ground and in space for a range of standard industry fuels, and our design allows for a very simple and non-invasive addition to any fluid system, as it's a self-contained valve that's rated for high pressures. So this service would be available for any orbit and able to refuel any number of satellites with the help of depots, which store the extra fuel for the shuttle to refuel from for multiple satellites. The US has successfully flown a demonstration mission for this. And then in the UK, we are currently developing and qualifying our RAFTI and GRASP, including in-orbit experiments, as well as exploring the refueling of large telecommunication satellites with the missions team.
Cool. So why should we refuel in the first place? Boils down to three main points. Firstly, it increases the revenue potential. So that's essentially extending our spacecraft lifetime so that we don't have to keep sending new spacecrafts up in space. And also it allows the ending of the single-use paradigm. Now, next is to enhance spacecraft mobility. So that's essentially the point that we can reposition assets, and that offers flexibility. Secondly, it also enables the on-demand retasking of satellites, which is great because that increases adaptability. And lastly, it enables new operations and business models. So that's essentially being able to open a whole new world of novel capabilities, spacecrafts, orbits, where fuel capacity is perhaps not as tight of a constraint. And lastly, it allows sustainable missions such as ADR, active debris removal. And now, to expand on sustainability, the primary benefit is breaking the single-use paradigm. So essentially, that's allowing satellites to be reusable, like planes, cars, and also launch vehicles. Reusability also helps us to reduce our big problem of space debris, and it opens more choices for end-of-life decisions. And also, active debris removal is great. We can apply this technology to ADR missions, overall greatly benefiting space sustainability as a whole. Last but not least, it makes us happy and proud to be working here. And with that, I'd like to end. Thank you very much.
Fantastic. Thank you very much. That's really, really entertaining. Any questions from the room? Yes, fantastic.
Thank you. Great presentation. So about active debris removal. So the same interface can be used for like catching and removing the spacecraft into the atmosphere, or what's the plan there?
Well, so our involvement with active debris missions, essentially being able to fuel spacecrafts that would allow you to do that. So having our technology being involved in the creation of these satellites would be really good on ground, and also that can be used later on in space as well.
Understood. Thank you.
Is this for a specific type of fuel to be used, or can it be adapted in the future as fuel types change and maybe for multiple fuel types at the same time?
Yeah, so we are qualifying for multiple fuels. The US version is mostly hydrazine, but here in the UK, we're looking at a lot of varied high pressure fuels. So a lot of the main ones for electric propulsion, like xenon, Krypton and other. So we're trying to make it as open as possible to support as many satellites as possible.
Fantastic. Let's have one final round of applause for OrbitFab, please. Fantastic. So that brings us to the end of our lightning talk session. I'll just pop this on the slide here just to get you all excited. A few notes before lunch. For anyone that's not got their conference badge, please come and speak to us at the front desk in the visitor centre in a moment. We'll get that sorted out. In terms of lunch, we would ask that anyone with dietary requirements and also anyone that is presenting a poster over lunch to get their food first, so they can get their food and then go and stand by their poster to start interacting and networking. If there's any questions or queries, I'll be on the front table in the visitor centre as well, and we will start gathering to move back across here just before 1 o'clock. But before we go, can I just ask for one big round of applause for all of our presenters from this session?